Buying used breakers and disconnect boxes presents both potential advantages and disadvantages. On the one hand, significant cost savings can be realized, as used components are typically much cheaper than new ones. Furthermore, used markets may offer access to older or discontinued models that are no longer manufactured, and reusing these items contributes to environmental sustainability by reducing waste. Many used breakers and disconnect boxes have been inspected and tested, increasing the likelihood that they will function as expected if properly installed. However, there are notable safety concerns, as used components may have sustained damage or been altered, potentially creating hazards. Used items usually lack warranties, leaving buyers without recourse if premature failure occurs. Compatibility issues can also arise if used breakers or disconnect boxes are mismatched with the existing electrical system, possibly leading to malfunctions or electrical fires. The risk of encountering counterfeit products, which may not meet safety standards, further amplifies the chance of electrical accident. To mitigate these risks when considering used breakers and disconnect boxes, carefully inspect the components for any signs of damage, tampering, or wear before purchase. If possible, test them to ensure proper functionality before installation. Purchase used electrical components only from reputable suppliers known for selling quality used items. For safety reasons, it is strongly advisable to have a licensed electrician handle the installation of breakers and disconnect boxes. Focusing on good experiences with used breakers and disconnect boxes, one can realize cost savings because used breakers and disconnect boxes can be significantly cheaper than new ones, saving money on electrical upgrades or repairs. Additionally, the availability of discontinued models can be beneficial. Some older or discontinued breaker models may only be available used, which can be helpful if one needs to replace a specific component. Environmental benefits also exist in that reusing used breakers and disconnect boxes helps reduce waste and promote sustainability. Furthermore, many used breakers and disconnect boxes have been inspected and tested, so they are likely to function as expected when installed correctly. Now, considering bad experiences with used breakers and disconnect boxes, one faces safety concerns. Used breakers or disconnect boxes may have been damaged or altered in the past, posing a safety hazard. It's crucial to inspect and test any used electrical components before installing them. Also, warranty issues are problematic because used breakers and disconnect boxes typically do not come with any warranty, so there may be no recourse if they fail prematurely. Furthermore, compatibility problems exist because used breakers or disconnect boxes may not be compatible with a specific electrical system, leading to potential malfunctions or electrical fires. Also, counterfeits are a concern. Counterfeit breakers and disconnect boxes may look genuine but may not meet safety standards, increasing the risk of electrical accidents. To navigate the cautions when buying used breakers and disconnect boxes, firstly, inspect carefully. Before purchasing, thoroughly inspect the breakers and disconnect boxes for any signs of damage, tampering, or wear. Secondly, test for functionality. If possible, test the breakers and disconnect boxes to ensure they are working properly before installing them. Thirdly, purchase from reputable sources. Buy used breakers and disconnect boxes from reliable suppliers who have a good reputation for selling quality used electrical components. For safety reasons, it's advisable to have breakers and disconnect boxes installed by a licensed electrician. Regarding electrical safety, it is important to understand several aspects. Electrical safety is paramount when dealing with any electrical system, whether it involves new or used components. Working with electricity always carries inherent risks, including the potential for electric shock, arc flash, and electrical fires. To ensure safety, it's essential to follow established safety procedures and guidelines, adhere to relevant electrical codes, and use appropriate personal protective equipment (PPE). Firstly, to energize circuits. Before working on any electrical circuit or equipment, always de-energize the circuit by turning off the corresponding circuit breaker or disconnecting the power source. Verify that the circuit is de-energized using a reliable voltage tester. Secondly, use proper PPE. Wear appropriate PPE such as insulated gloves, safety glasses, and arc-rated clothing to protect against electrical hazards. Thirdly, inspect equipment. Regularly inspect electrical equipment and tools for any signs of damage or wear. Replace or repair damaged equipment immediately. Fourthly, follow lockout-tagout procedures. Implement lockout-tagout procedures to prevent accidental re-energization of circuits during maintenance or repair work. Fifthly, maintain a safe work environment. Keep the work area clean and free of clutter. Avoid working in wet or damp conditions. Sixthly, use insulated tools. Use tools with insulated handles to prevent electrical shock. Seventhly, never bypass safety devices. Never bypass or disable safety devices, such as ground fault circuit interrupters GFCIs or arc fault circuit interrupters of size. Eighthly, be aware of overhead power lines. When working outdoors, be aware of overhead power lines and maintain a safe distance from them. Ninthly, follow electrical codes. Adhere to all applicable electrical codes and regulations, such as the National Electrical Code NEC. Tenthly, seek professional help. If you are not qualified to perform electrical work, seek assistance from a licensed electrician. Regarding the National Electrical Code or NEC, the NEC is a comprehensive set of standards for electrical installations in the United States. It provides guidelines for safe and reliable electrical systems. The NEC is updated every 3 years to incorporate new technologies and address emerging safety concerns. Several key areas covered by the NEC are firstly, wiring methods. The NEC specifies acceptable wiring methods for various applications, including the type and size of conductors, raceways, and cables. Secondly, overcurrent protection. The NEC requires overcurrent protection devices, such as circuit breakers and fuses to protect against overloads and short circuits. Thirdly, grounding and bonding. The NEC mandates proper grounding and bonding of electrical systems to minimize the risk of electric shock and ensure proper operation of equipment. Fourthly, equipment installation. The NEC provides guidelines for the installation of electrical equipment, such as receptacles, switches, and lighting fixtures. Fifthly, special occupancies. The NEC includes specific requirements for electrical installations and special occupancies, such as hazardous locations, healthcare facilities, and swimming pools. Sixthly, low voltage systems. The NEC addresses the installation of low-voltage systems, such as fire alarm systems, communication systems, and control circuits. Seventhly, renewable energy systems. The NEC covers the installation of renewable energy systems, such as solar photovoltaic PV systems and wind turbines. Eighthly, emergency systems. The NEC includes requirements for emergency power systems, such as generators and uninterruptible power supplies UPS. Ninthly, wiring of appliances. The NEC provides guidelines for the wiring of appliances, such as refrigerators, ovens, and washing machines. Tenthly, inspections and testing. The NEC requires electrical installations to be inspected and tested to ensure compliance with safety standards. Here's additional information about breakers and disconnects. Circuit breakers and disconnects are essential components of electrical systems, providing overcurrent protection and means of disconnecting power for maintenance or emergencies. Breakers are automatic switches that interrupt the flow of electricity when a fault or overload occurs, protecting circuits and equipment from damage. Disconnects are manually operated switches used to isolate electrical circuits or equipment from the power source. Firstly, types of circuit breakers. There are several types of circuit breakers, including thermal magnetic breakers, which use a bimetallic strip and an electromagnet to trip the breaker, instantaneous trip breakers, which trip very quickly in response to high fault currents, ground fault circuit interrupters GFCIs, which protect against ground faults, and arc fault circuit interrupters of size, which protect against arc faults. Secondly, types of disconnects. There are several types of disconnects, including fused disconnects, which incorporate fuses for overcurrent protection, non-fused disconnects, which do not provide overcurrent protection, and safety switches, which are used to disconnect power to equipment for maintenance or repair. Thirdly, breaker and disconnect ratings. Breakers and disconnects are rated for voltage, current, and interrupting capacity. Voltage rating indicates the maximum voltage the device can safely handle. Current rating indicates the maximum continuous current the device can carry. Interrupting capacity indicates the maximum fault current the device can safely interrupt. Fourthly, breaker and disconnect applications. Breakers and disconnects are used in a wide range of applications, including residential, commercial, and industrial electrical systems. They are used to protect circuits and equipment from overloads, short circuits, and ground faults. Fifthly, breaker and disconnect selection. When selecting breakers and disconnects, it is important to consider the voltage, current, and interrupting capacity requirements of the circuit or equipment being protected. It is also important to select devices that are appropriate for the environmental conditions in which they will be used. Sixthly, breaker and disconnect installation. Breakers and disconnects should be installed by qualified electricians in accordance with applicable electrical codes and standards. Proper installation is essential for ensuring safe and reliable operation. Seventhly, breaker and disconnect maintenance. Breakers and disconnects should be regularly inspected and maintained to ensure they are functioning properly. Maintenance may include cleaning, tightening connections, and testing operation. Eighthly, breaker and disconnect troubleshooting. If a breaker trips or a disconnect fails to operate, it is important to troubleshoot the problem to identify the cause. Common causes of breaker trips include overloads, short circuits, and ground faults. Ninthly, breaker and disconnect safety. Always de-energize circuits before working on breakers or disconnects. Use appropriate personal protective equipment (PPE) such as insulated gloves and safety glasses. Tenthly, breaker and disconnect codes and standards. Breakers and disconnects must comply with applicable electrical codes and standards such as the National Electrical Code (NEC) and Underwriters Laboratories UL standards. Let's look at NEC tables. The NEC contains numerous tables that provide guidance on conductor sizing, overcurrent protection, and other aspects of electrical installations. These tables are essential for ensuring safe and compliant electrical systems. Firstly, Table 310.15b16. This table provides ampacity ratings for conductors based on insulation type, conductor size, and ambient temperature. Secondly, Table 250.122. This table provides minimum equipment grounding conductor sizes for various overcurrent device ratings. Thirdly, Table 430.52. This table provides maximum ratings or settings for motor branch circuit, short circuit, and ground fault protective devices. Fourthly, Table 310.16. This table lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current carrying conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius. Fifthly, Table 250.66. This table provides grounding electrode conductor size for alternating current systems. Sixthly, Table 314.16a. This table provides the number of conductors allowed in outlet device and junction boxes. Seventhly, Table 430.250. This table provides full load current in amperes direct current motors. Eighthly, Table 430.248. This table provides full load currents in amperes, single-phase alternating current motors. Ninthly, Table 430.251a. This table provides full load current in amperes, two-phase alternating current motors, 4-wire. Tenthly, Table 430.252. This table provides full load current in amperes, three-phase alternating current motors. Here's additional guidance on working with electricity. Working with electricity can be dangerous if proper precautions are not taken. It is important to understand the risks involved and follow established safety procedures. Firstly, electrical shock. Electrical shock occurs when a person comes into contact with an energized conductor and a path to ground. The severity of the shock depends on the voltage, current, and duration of contact. Electrical shock can cause burns, muscle contractions, cardiac arrest, and death. Secondly, arc flash. Arc flash is a dangerous electrical explosion that occurs when a short circuit or fault creates a high-energy arc. Arc flash can cause severe burns, blindness, and death. Thirdly, electrical fires. Electrical fires can be caused by overloaded circuits, short circuits, or faulty equipment. Electrical fires can spread quickly and cause significant damage. Fourthly, grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent device and preventing electrical shock. Bonding connects metal parts of an electrical system to create a low impedance path for fault current. Fifthly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, protect against overloads and short circuits. These devices interrupt the flow of electricity when a fault occurs, preventing damage to equipment and reducing the risk of electrical fires. Sixthly, personal protective equipment (PPE). PPE is essential for protecting workers from electrical hazards. PPE includes insulated gloves, safety glasses, arc-rated clothing, and footwear. Seventhly, lockout-tagout. Lockout-tagout procedures are used to prevent accidental re-energization of circuits during maintenance or repair work. These procedures involve disconnecting the power source and placing a lock and tag on the disconnecting means to prevent it from being turned back on. Eighthly, electrical codes and standards. Electrical work must comply with applicable electrical codes and standards, such as the National Electrical Code (NEC) and Underwriters Laboratories (UL) standards. These codes and standards provide guidelines for safe and reliable electrical installations. Ninthly, qualified electricians. Electrical work should be performed by qualified electricians who have the knowledge, skills, and experience to perform the work safely and correctly. Tenthly, continuous learning. Stay updated on the latest electrical codes, standards, and safety procedures. Attend training courses and seminars to enhance your knowledge and skills. If you are not comfortable working with electricity, seek help from a licensed electrician. Understanding voltage, amperage, and resistance are key elements to electrical work. Firstly, voltage. Voltage is the electrical potential difference between 2 points in a circuit. It is the driving force that pushes electrons through the circuit. Voltage is measured in volts. Secondly, amperage. Amperage is the measure of the electrical current flowing through a circuit. It is the rate at which electrons flow past a given point. Amperage is measured in amps. Thirdly, resistance. Resistance is the opposition to the flow of electrical current in a circuit. It is measured in ohms. Fourthly, Ohm's law. Ohm's law states that the voltage in a circuit is equal to the current multiplied by the resistance. This relationship is expressed by the formula voltage equals current times resistance, or volts equals amps times ohms. Fifthly, power. Electrical power is the rate at which electrical energy is transferred in a circuit. It is calculated by multiplying the voltage by the current. Power is measured in watts. Sixthly, series circuits. In a series circuit, the components are connected end to end, forming a single path for current to flow. The total resistance in a series circuit is equal to the sum of the individual resistances. The current is the same throughout the series circuit, while the voltage is divided among the components. Seventhly, parallel circuits. In a parallel circuit, the components are connected side by side, providing multiple paths for current to flow. The total resistance in a parallel circuit is less than the smallest individual resistance. The voltage is the same across all components in a parallel circuit, while the current is divided among the branches. Eighthly, AC versus DC. Alternating current AC is a type of electrical current that periodically reverses direction. Direct current DC is a type of electrical current that flows in one direction only. AC is used for most power distribution systems, while DC is used in batteries and electronic devices. Ninthly, transformers. Transformers are used to increase or decrease the voltage of alternating current. Step-up transformers increase the voltage, while step-down transformers decrease the voltage. Transformers are essential for efficient power transmission and distribution. 10th, electrical safety. Always follow safe work practices when working with electricity. To energize circuits before working on them, use insulated tools, and wear appropriate personal protective equipment (PPE). If you are not comfortable working with electricity, seek help from a licensed electrician. Ground fault circuit interrupters or GFCIs are critical safety devices in electrical systems, designed to protect people from electric shock. A GFCI monitors the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the hot and neutral conductors, it indicates that some current is leaking to ground, which could be flowing through a person. The GFCI quickly interrupts the circuit, preventing a dangerous electric shock. GFCIs are required in areas where there is a high risk of contact with water, such as bathrooms, kitchens, and outdoor locations. Here's some additional info about arc fault circuit interrupters or SIs. SIs are another type of safety device that protects against electrical fires. SIs detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur due to damaged wiring, loose connections, or other electrical problems. When an SI detects an arc fault, it quickly interrupts the circuit, preventing a fire from starting. SIs are required in many residential circuits, such as bedrooms, living rooms, and dining rooms.